Today we want to have a look at groundwater, seepage and dewatering analysis. Per se, we just want to see what happens when we have water present in our formation. So all throughout our discussion, we are talking about the strength of the rock, but then water is one of the parameters or the things that can disturb our rock or soil as geotechnical officers. And so for that reason, we need to know how does even water behave within the soil? How is water transported from one point to the other? So we'll look at some brief computations and then some theoretical assumptions regarding the movement of water through our rock and that of the soil. So we'll look at that and then maybe end the lecture by looking at how this water we are discussing can affect our slopes when it is present. And then we end the class for the day. Yeah. So we are trying to have a look at groundwater. So water is one of the key things that as geotechnical officers, we do not like to see. Yes, they say water is life, and in fact, it is life. However, we don't want to see it at certain places or at certain times of our lives. We don't want to have water disturbing our designs. And so we want to know and understand how water, when present in our designs, can affect us and how we can compute and have a prior knowledge as to the water. For example, if I am trying to come up with a tailings dam, I need to understand the water table at that section and how the material there allows water, the rate at which it can allow water into that tailings dam, so that I will know what type of sealing material I should use to prevent the water from coming into the distance. And sometimes too, I need to understand that behavior of the formation that allows the flow of water through it, so that in my pit, I can do other things, put in certain measures to help me know how many pumps or pipes I need at a given time to be able to handle the water and the rate of flow of water into my pit or my underground operations. And so there is that need for us to understand the travel of water through our material. So we're saying that the flow of groundwater is known to be through the interconnected space. So whatever a material is, so for example, if I have a rock material and this rock material happens to be porous, already because it is porous means that it is allowing some quantity of space that can accommodate water. But mind you, the fact that there is that empty spaces within the material does not warrant the flow of water. So the key word here is interconnectivity, the interconnection. So if I have pores within a rock sample or any given sample of material, and these pore spaces are not connected, it can only sometimes store the water, but it cannot allow the flow of the water. So this is to let us understand that porosity does not always mean high permeability. Let's get this clear. So the key word here is the interconnected pore spaces between the particles and in one hand. And then when we are talking about rock, if our rock is not all that porous, then sometimes the discontinuities in the rock material can also allow the flow of water. So often the flow of groundwater through a confined or unconfined porous material can be presented or represented in a uniform flow. So the flow in water, in soil or in rock material, obviously cannot be like the one you see at the seashore, where there are waves, tidal waves back and forth. No. But then when we are making assumptions for computations of our water, the flow of water through this medium, which is the soil or the rock, we are considering a laminar flow, which means the flow is stable and quite smooth. It is not turbulent. And these are the conditions we have to understand. So the term seepage flow, is used to describe the movement of water through or under the soil structures to wells, drains, and then other reservoir. So if water will move from one point to another, it is through seepage. Then generally the Reynolds number. So some theories or certain people who are the founding fathers of fluid mechanics came up with a formula and other ways you can determine whether a particular flow is laminar or turbulent. And so we always look out for a Reynolds number of 1, which we can use to say that if your flow, the Reynolds number is determined in your fluid mechanics, and you say that, okay, it is less than 1, then we say that the particular flow we are considering is laminar. And so this comes to play. And then when that Reynolds value is determined to be laminar, then we can adopt somebody's principle. The person is known as Darcy. So he proposed a certain law that we use today when we are dealing with flow of water or flow of fluid through certain mediums, and that is the Darcy's law. So a simplified theoretical and numerical approach is developed and applied to practical examples to obtain flow nets that describe the flow rate. So this is not a soil mechanics class. Otherwise, we would have delved deeper into what we term as a flow net. It is a practical approach or a graphical approach that helps us to determine the flow path of water. When water is moving from one medium, it could be a higher elevation to a lower elevation. It is moving from one part of a building to the other part of the building. The travel of water, people have come up with these seepage or this flow net analysis to help us to be able to compute the pressure drops or the equipotentials as water flow through these mediums. And at some point, we are able to determine the rate of flow of water in a given medium. And so we are not going into the flow net activities for this particular class because it's not a soil mechanics class. Then we have, this is followed by a description of test methods. So sometimes in the laboratory too, we conduct a test. So let's take, for example, you are an officer in charge of geotechnical activities in your mine, and you want to find out, you want to, let's say, for example, you are thinking of pumping water from an active pit to another pit, perhaps that has been abandoned, but they are closer. So you may want to know the rate of flow of water through this particular material, because that wall that will be dividing where you are dumping the water and where you are pumping the water from, you need to know. Otherwise, you may end up doing cost 90 job because you pump the water there and in the next day or within some few minutes, they find themselves back in there. So you may want to pick some samples of the rock material, bring it to our geotechnical laboratory to do the testing, to tell you the permeability constant of the material. And this can help you determine the rate of flow. You can use this parameter to calculate the quantities of water to expect from nearby wells and nearby streams and whatever within your mining area, and even to tell you whether your water can move from the dumping location to the pit where you are pumping the water out. So there is that need to do some laboratory tests, which we term as the constant head test. Okay, the constant head test or the falling head test. These are tests that can be conducted on samples to determine their permeability constants. Then the flow rate through water flows through soil or rock in various ways depending on the nature of the ground. Yes, this is a fact that if I have a sandy soil or a shale or a granite or a sedimentary rock per se, if I have any sedimentary rock or a metamorphic rock or a granite rock, depending on that type of material, it can influence the rate of flow in that, the flow of water, given the medium we are considering. And so we have to bear that in mind, that you go to mine A and they are dealing with sedimentary rock, the behavior of flow will be different from when you get to mine B and they are dealing with a kind of an igneous rock. And so the nature of the ground can also be a contributing factor that will affect the behavior of flow. Then water transmitting soil or rock units are called aquifers. So aquifer is just a rock term that is able to store water and allow the flow of water through it. It's a type of rock or a particular medium through which water can be transmitted. And so aquifer, we have the confined one and unconfined one. So an aquifer is said to be confined when around that rock that is containing the water, it does not allow, it is enclosed such that water can't find its way escaping through any other medium. And this happens usually where it becomes detrimental, where you do a project and you are unable to tell whether there is a water transmitting rock of that sort there. And let's say you do drilling and by accident you encounter it. You see the water dashing out as if it is a spring. Why? Because it has been contained in there for a long time and it has more or less harnessed a lot of pressure. And so when you give it the slightest opening, the water begins to shoot out. So those are the mediums we are talking of. So different types of aquifer demonstrate different modes of groundwater flow. So if my water is flowing through, the flow behavior within my mine is such that the water is coming from an aquifer, then I should be expecting more water than someone who is just within a zone where you don't have anything of that sort to deal with. And so such as intergranular fissure and then conduit flow. So depending on the type of material you are handling, you may be having different types of behavior in terms of your flow.